All right, dot product. Now, I don't want to go too far into dot product, but I kind of want to make sure we have a sense of what it's doing, what it's talking about, just to try to give us a little bit of context. Then we'll talk about some of its mechanics. So, there are two nice metaphors for multiplication. They are repeated adding, repeated addition. That's essentially what our scalar multiplication is. One of the other nice metaphors for multiplication, one of the things we think about when we talk about multiplication, is finding an area. If you got so many squares in this direction, then so many squares in that direction, multiplication gives you area. And the cross product is really doing a lot of, fits that metaphor for multiplication pretty well. Unfortunately, the dot product, its best metaphor is really the physics concept of work. But unless you've taken some physics and dealt with work, that metaphor isn't going to help any. And about the only other good metaphor is signed numbers. But we just have to start thinking about signed numbers happening in multiple dimensions. So let me try to give you some indication of what the dot product is doing. So in terms of signed numbers, if we think of 3 being multiplied by -4, well, let's just start with 3 times 4. Good old school 3 times 4, we think 3 times 4 should be 12, and it is 12, and the dot product doesn't change that. 3 times 4 is still going to be 12. 3 dotted with -4 is just what we think it should be. It's -12, and that doesn't change when we talk about dot product. If we take -3 and multiply by +4, we know we get -12. And the one that often weirds people out a little bit early on, if we take -3 and dot it with -4, we somehow got back to +12. Now, you deal with this long enough and it starts to become natural, and after a while you don't even really question it. And, we often think of it in terms of, removing, that negative is talking about removing negativity. So if we remove a bunch of negativity, we get positivity. And, we can kind of justify to ourselves that this has to be true. But the idea of dot product actually gives us, in some ways, a little bit more insight. Because what dot product does is it considers 2 vectors. So, got a vector here of magnitude 3 and another vector here of magnitude 4. So, magnitude 4. So I'm even going to be real specific here. The magnitude of v is 3, and the magnitude of this other vector u is 4. So their dot product, v dotted with u, we'd like that dot product to equal 12. And the nice thing is, it will equal 12 as long as these 2 vectors are pointed in the same direction, like they are. As I mentioned in one of the other videos, dot product does give us the product of the magnitudes, but it scales it by how well the 2 vectors are working in concert. If the vectors are parallel, headed in the same direction, then the dot product does give us just the product of the magnitudes, just like we'd want it to. But if instead we had a vector u, again, I'm going to make its magnitude 4, and another vector whose magnitude was again still 3. But notice now they're not headed in the same direction. They're headed kind of in the same direction, but they're not working together perfectly. Or this vector isn't working exactly in line with this other vector. Now, we can still take a dot product, and because they're kind of working together, that dot product is going to be positive, so it's going to be greater than 0. But because of the lack of efficiency, because they're not working in perfect concert with each other, their dot product is going to be less than 12. There's going to be some loss to it. And we'll talk about, in a second, we'll talk about finding exactly what it is, depending on the vectors. But the key is that we get that loss because they're not working exactly in line with each other. If we go one step further and we talk about that vector u, again, the magnitude of that vector u is still going to be 4. But the other vector, which is still going to have a magnitude of 3, is perpendicular to it. Perpendicular is a dangerous word. Perpendicular, technically, they have to cross each other. The fancy word is orthogonal. Orthogonal means perpendicular without having to cross or be in the same plane. It's a more general term, but it means essentially perpendicular. It means what you think of when you think of perpendicular. So that's I don't know if your book uses that vocabulary here, but it's a vocabulary you'll have to get used to when you start dealing more and more with vectors. So if two vectors are perpendicular or orthogonal, well, these vectors, we can still take a dot product. We can take a dot product as long as they're both vectors. That dot product, again, though, gives us a value based on how these two vectors are working with each other. And these two vectors aren't working with each other at all. They're not working against each other. They're not pulling in opposite directions. They're just pulling in, well, orthogonal directions, completely different directions. I mentioned work. You can imagine if you were trying to pull something. If you were trying to pull 3 pounds of force in this direction, well, you would do as much work as you possibly could. All the work of pulling is pulling it in the direction of this vector u. So all of your force is going in that direction. Imagine pulling a cart. Say there was a little cart that you were pulling down a track. If you're pulling in the same direction as the track, then all of your work is producing product. If you were pulling at a slightly different angle, well, the cart would still move forward, but you'd be wasting some of your effort. That's this waste. If there was a cart on this track and you were pulling orthogonal to the track, that's not going to move at all. So that dot product is going to be 0. They're not working against each other, but they're not working in concert at all. What if they were working against each other some? So magnitude 4 vector again, but now the other vector, still magnitude 3. So it's not headed in exactly the opposite direction, so it's not working against it as much as it could, but it's still pulling the other way. So it's going to be negative, their dot product, because they're pulling against each other, but it's not going to be the full negative 12 that we could get if they were working in perfect opposition. We don't get that negative 12 unless they're headed purely in opposite directions. So if we had 4 and 3, they're heading in opposite directions. Now their product, their dot product, would be that negative 12. Now, you might be thinking, well, doesn't that make this negative 3? Well, that's the idea of negatives. If you've got 0, 1, 2, 3, 4 there, and 1, 2, negative 3, well, that's your 4. That's got a magnitude of 4. Well, the other vector has a magnitude of 3. That's its magnitude. The negative is expressing direction. So because the positive 4 and the negative 3 are headed in different directions, their product is negative. Same thing if we had positive 3 and negative 4. They're headed in opposite directions. But what happens if we have essentially a vector whose magnitude was 3, headed in what we think of as a negative direction, and then another vector whose magnitude is 4 headed in what we think of as a negative direction? Well, now their dot product, because they're headed in the same direction, goes back to being positive. And that would happen no matter what that direction is. If this had a magnitude of 4 and that had a magnitude of 3, then the dot product between those two vectors would be, would be 12, would be the full product of their magnitudes. If they form an acute angle, then they're kind of working together, but not quite. It's going to be less than 12. If they're orthogonal, if they're at exactly right angles to each other, then the dot product is 0. If they're obtuse to each other, the dot product is negative. But not the full negative product of their magnitudes unless they're headed in completely parallel opposite directions. Now the dot product is negative 12. So that's kind of a primer on what the dot product is telling us. It's finding a product, so it means the same thing a lot of multiplication kinds of problems mean, but it's accounting for the loss in efficiency of the vectors not working in concert with each other. So that's one thing I want you to keep in mind. Now, how to find a dot product? There are two ways to find a dot product. And I want to show you, plus 5j, kind of why they work the way they do. So here's one vector, and I want to dot that with another vector. Say 2i minus 7j. Doesn't really matter. Now, if this was just x's and y's and numbers and we were multiplying, we would know we have to FOIL this together. And really, that's what dot product is. It's the multiplying these things together. So we'd have the 3i multiplied by this 2i plus the inners, say 5j multiplied by 2i, and then the outers, so I'm going to take that negative, so 3i multiplied by 7j j. And then the last one's still positive times a negative. I'm going to keep that negative here. 5j times 7j. And that's essentially still true for multiplying, for finding a dot product. But here's the issue. Notice these are both i's, so they're both headed in the I direction. So this product is just the product of the magnitudes because they're headed in the same direction. So 3i times, or dotted with, ooh, that almost made me mad at myself. These are all still dot products. I used juxtaposition, can't do that. So this is still just 6. But here, I and j are orthogonal to each other. They're perpendicular. So their dot product is 0. Here, I and j are orthogonal, so their dot product is 0. In the last piece, we got j and j again. These are headed again in the same direction. So 5j dotted with 7j is going to be the 35, and that negative will go with it because they're technically headed in opposite directions. So we get 6 minus 35, or negative 29. So when you look at our rule for how do we find a dot product, it says, well, we just multiply the like components, multiply the first components together, and then multiply the second components together. Well, we know in multiplying we should have 4 terms, but the I, j, j, I terms, they're always going to be 0 because of the orthogonality. So we never have to do that. If you end up having a dot product that you have to find, you don't bother with the full FOIL. You just take the like components, the I components, multiply them together, take the j components, multiply them together, and add those. You don't have to go through all of this extra notational work. So it's handy, but it's nice to see why, I think. So even if we had something in position vector form, say 3, negative 5, and we wanted to dot that with, 6, 9, why not? We could write it in IJ form and perform all the FOIL and simplify it if we wanted to, but that dot product really is just the sum of the products of the magnitudes. So 18 plus negative 45, or 18 minus 45, which is what, 27? Now, what that 27 represents depends on what your vectors are. So if you've got, say, force and distance, then we're talking about work. If we've got, oh God, so many, but don't worry about that yet. It depends on what the objects are. Right now, we're just going to kind of stick with the mechanic. Work is the good example, though. So if this is so many pounds of force and this is so many feet of movement in a particular direction, then we got 27 foot-pounds of work. So work is good. That's the best example, really, and about the only one we're going to work with. So that's one tool for finding a dot product. The other nice tool about dot product, I want to build that one. This is why I wanted another video on dot product. So that's one formula for dot product. If you've got I'm going to use position vector form. If you've got A, B dotted with CD, then your dot product is like components multiplied together, find the sum. So that's one rule for dot products. But if you think about that angle argument that I was making before, if this is our vector u, and we have another vector v, come on. No, it's not working. The one time I want it to work. Okay. So remember, if they're going in the same direction, like they are right now, then the product is equal to the product of the magnitude, the full 100% of the product of the magnitude. As we angle away, we get less and less and less and less, down to a 0 at 90 degrees, or at pi over 2 radians. And then we get negative, bigger and bigger and bigger, until we get to 100% negative when they're pointing in the opposite direction. We know something that already does that. When the angle between them is 0, we get 100% of the angle between them, or 100% of the product of the magnitudes. And then as we get towards 90 degrees, it becomes 0. If we're facing 90 degrees, the dot product is 0. Then as we get larger, we're negative, so we're now negative, and we max out at the negative 100% of the magnitude. Well, gosh, that's a function we should recognize. That's cosine. So the other way to look at the dot product, other than this sum of components, is that our dot product should equal the product of our magnitudes, the magnitude of v multiplied by the magnitude of u, but it's lessened by the cosine of the angle between the two vectors. So sometimes it's nice to find dot product this way. If you have components, find the dot product this way. Multiply like components, add them together, boom, you have a dot product. But if we know the magnitudes of our two vectors, and we know the directions that they're headed, so we can figure out what the angle between them is, then finding the dot product by the cosine times the product of the magnitude is a very nice tool. Even better, if we divide off these magnitudes, we get that the cosine of the angle between our vectors is the dot product divided by the product of the magnitudes, which gives us a tool for finding the angle between vectors. And that's a very nice use of our dot product. So, for example, given these two vectors, if we want to find the angle between the two vectors, well, if we take the dot product and divide by the product of the magnitudes, we know that has to equal the cosine of the angle between them, a little cosine inverse, and we'll have the angle. So the first thing we need is the dot product. So negative 3i plus 4j. We're going to dot that. Notice these are all normal parentheses because I'm not saying, I'm not writing it as a position vector. I'm just using the parentheses to break up where the dot product is. And then 5i plus 12j. So our dot product will just be, again, product of like components. So negative 15 plus 48, which is what, 33? Is that right? 33? Yeah, 33. So that's our dot product. And what is that in ratio to the product of the magnitudes? Well, we'd need the magnitudes, but the magnitude of V, well, it's a 3, 4, 5 right triangle, so it's 5. The magnitude of U, well, that's our 5, 12, 13 triangle, so these are just trying to be nice here, 5 and 13. So the product of the magnitudes is 5 times 13, so it's 65. So you can think of it as, these magnitudes, the magnitude of 5 and the magnitude of 13, their product wants to be 65. But the vectors are not headed in the same direction. This one's headed, that way and up, so it's going that way. This one's going that way and up, so it's, up a lot more than that. So that way. So these vectors, if they were working in perfect concert, they produce 65 units of whatever. But they're not working in perfect concert. They're only producing 33 because of that angle between them. And we can use cosine to find what that angle is. So that angle theta will be the cosine inverse of 33/65. And I know what you're going to say, or I hope I know what you're going to say. You're going to say, but that's supposed to give us 2 answers in the first rotation. It's not just going to be the one. Well, what is the cosine inverse of 33/65? It's about 60-ish. It's a little less than 60. It's at 59 degrees. I should probably check, but I'm not going to. But somewhere around 59 degrees, maybe 61 degrees, I don't know, somewhere around there. Yeah. But it's also going to give us, we know cosine gives us 2 answers, right? So 59 degrees, but there's also going to be the answer down here, which would be, 301 degrees. So it might seem like, hey, what are we going to do with those 2 answers? Well, the 2 answers are natural to this problem. The small angle between them is always going to be your principal, that 59 degrees. Well, where's the 301? The 301 is this angle. So generally when we talk about the angle between 2 vectors, we mean the smaller of them, because there's always going to be 2 angles, one the short way and one the long way. So generally, find the angle between 2 vectors wants the short one, and the cosine inverse is going to be naturally the shorter of the 2. But there are a lot of applications where we want that other angle, so it's good to know we always get it. Heck, we even always get the coterminals. But we don't care about those because we're just looking for the smaller angle between them. But yeah, this relationship is very nice and is a nice kind of way to think about all this stuff that is happening with these angles going in different directions. What the dot product is telling us is it's telling us, I don't like that these are separated. They're fine separated, but it's nicer to do it this way. It's telling us the difference between the dot product and the product it wants is dependent on how well they're working together, how well they're pointed in the same direction. Hopefully that gives you some context on what dot product even is. So an example, you'll have a lot of examples with, airplanes flying and wind, and you'll have to take the airplane and add it to the wind, or take your ground speed and ground heading and subtract the wind from that to get the bearing that the plane should be on. You'll have a lot of application questions like that. And you'll often be given your information in terms of the airplane flying at a particular speed at a particular bearing. And you'll want to turn that into a vector in either component form, position vector form, so you can add it to the wind or subtract it or do whatever you're supposed to be doing with it. So a couple things I want to make sure you're happy with before I let you go is that when you talk about an airplane's speed and its bearing, that is not the speed and bearing of the airplane with respect to the ground. It's the speed and bearing of the airplane with respect to the air around it. And often that can be quite different. Essentially, an airplane only knows how fast it's going by measuring how quickly is it passing through the air it's in. So if it's flying at 200 miles an hour from its instruments, but there's a tailwind that's pushing the airplane at 50 miles an hour, then the plane might think it's going 200 miles an hour, but it's actually moving with respect to the ground at 250 miles per hour. It's getting a boost from that tailwind. Also, if you set your heading at due west, but you've got a crosswind, that crosswind is going to push you off course. So you might be pointing due west, but the plane isn't necessarily going due west unless you account for the wind. Think of it like swimming across, or swimming in a fast-moving river. You might think you're swimming very slowly, but you can be moving quite fast with respect to the shore because you're in a fluid that's moving really fast. You might think you're swimming directly toward the dock, but you're not headed directly toward the dock. You're heading at an angle because you're getting pushed by the water. Water and air essentially handle things moving through it in the same way. So when it talks about what the plane is doing, it's from the plane's perspective. So we're often asked, given the plane is doing this and the wind is doing this, what's the ground speed and ground heading? That means the plane and the wind together. So how is it moving with respect to some object on the ground? And if everything was pointed in the same direction, or opposite directions, you'd just be adding or subtracting. You're going 200 miles an hour, and you got a 50 mile an hour tailwind, you're going to be going 250 miles an hour. Great. If you've got a 200 mile an hour plane and you're getting a 50 mile an hour headwind, then you're going to be going 150 miles an hour with respect to the ground. But that all only works if the wind and the plane are going in exactly parallel directions to each other. When they start going at weird angles, well, our dot products and our cross products and all those things start to, well, our dot products anyway, and our adding and subtracting vectors all come into play. So, with all that in mind, how do we build a vector for this plane? Well, since we're given information in magnitude and direction, trigonometric form is usually the nicest way to go. And we know we've got essentially a formula for that. Our magnitude times the cosine of the angle of our direction in the I plus the sine of the angle for our direction in the J. That's going to give us our vector. The thing we have to be able to do is convert our bearing information into this theta. And really, what we consider our angle, you can measure your angle from anywhere you want. The requirement is it has to be measured from the same place in the same direction for every aspect of your problem. So you can have, you can measure from north if you want to, as long as everything's measured from north. You can measure from east if you want to, as long as everything's measured from east in any particular problem. So I tend to recommend at this kind of stage in your experience, measure everything from standard position. Just by habit, put everything in standard position. Consider north, south, west, and east the way we normally would think of it. The north going up, south going down, west, left, and east to the right, just because that's intuitively where we want them to be. That means our I hat, our X coordinate, is going to be horizontal, so it's going to be our east-west, and our J is going to be our north-south. Now, while that's how we naturally think of them, that's not often how bearings are expressed. So when you see a set of bearings like this, learning to read it is fairly important. So you've got three pieces of information here. This says north 20 degrees east. So if the plane is bearing north 20 degrees east, that means that's the direction the plane is going. And it's describing where you face and how far you turn. So it's saying face north, and then turn 20 degrees towards the east. So face north and then turn 20 degrees towards the east. That's what an N 20 degrees E, north 20 degrees east, means. Generally, in bearings, you will either start north or south and then turn either east or west. So it could say, south 72 degrees west would mean face south and then turn 72 degrees towards the west. So you'd be going that way. So what it allows you to do is to communicate in terms of acute angles, whether you're facing north or south and want to turn east or west. Now, sometimes you'll hear somebody say face or bearing north 120 degrees east. And they go, okay, face north, turn 120 degrees towards the east, you're going this way. And that's totally reasonable. But south 60 degrees east would have been, nicer. So that's really all bearings are. Face a particular direction, turn that many degrees in that direction. But we want to express things in standard position because it's going to agree with our I's and J's. So in standard position, we would call that angle 70 degrees. So the angle that we want to use, the direction that we want to use for our vector in terms of our I and J, is that 70 degrees. So the vector for our plane has a magnitude of 200 miles per hour and a direction of cosine 70 degrees in the I and sine of 70 degrees in the J. So that's our trigonometric form for our vector. And that's, express velocity as a vector. That's our velocity as a vector. But if we were going to add wind or do other mechanics with it, it would probably be nicest to have it in component form. So have that as our I component, and then 200 sine 70 degrees as our J component, And we could come up with decimal approximations for those and have your vector in component form. That way, when you make your wind in whatever its component form is, you can add them together or subtract them, do whatever you want. Fair? So this is at the end here just because you'll be doing a fair amount of this kind of converting direction and magnitude into vectors in component form so you can perform your operations, but also just to kind of, in case you didn't know how to read bearings like that, that's how you read bearings like that. And I really do recommend put everything in standard position and you'll be safe. Yeah. Okay, hopefully that helps. This one was only 40 minutes, that's nice. Let your instructors know if you need anything, and have a beautiful day.